Recording running.
All right, welcome back everyone after the coffee break. So now we have our last speaker of the day, Roozbeh Hazrat, joining us from Western Sydney University. And let me just look it up. Roozbeh is talking about Sandpile models and Leavitt algebras. Thanks for coming, go ahead.
All right, thank you very much for the invitation. And I thought, because this is the last talk and everybody is kind of tired, I'm going to give a light and entertaining talk, maybe it's better. Okay, so for that, let me start with a puzzle. Okay, so it's called the math with puzzle. And you can ask this puzzle from your kids or primary school students, people on the street. So there is a crazy doctor, and he built 3 machines. So machine number 1, machine number 2, machine number 3. So the machine number 1, if you just plug a cat inside this machine, it gives you a dog. It just transforms that cat to a dog. Machine number 2, if you plug a dog, then it gives you a cat, a dog, and a rabbit. And machine number 3, if you plug a rabbit, it gives you a cat and a dog, okay? And the nice thing about these machines is that it also works backward. i.e., now, if you just push a cat and a dog and a rabbit inside this machine, you get a dog, so back and forth. And the puzzle is, the question is, if I give you a cat, can you use these machines back and forth and transform that into 4 cats? Okay, so simple enough, but I guess a nice puzzle. Now, I'm gonna, well, just leave it to you to get the solution. But eventually, I want to look at this and give a mathematical model to this. But before I do this, let me give you a little bit more complicated version of this. Now, another version. Again, you have these machines. Again, 3 machines. And this time, you are pushing 3 rabbits. So note that here, I always push 1 animal inside the machine, and I got a variety of animals. But this time, I'm pushing 3 rabbits, and I'm getting a cat and 2 dogs. And the other one, I'm pushing 3 cats inside, and I get 2 cats and a rabbit. And then the last one, I just send 2 dogs, and I get a cat and a rabbit. And the same question, but this time, if I give you 3 rabbits, can you use these machines back and forth and give me 3 cats? Okay, so far, again, I think it's a fun puzzle. And I remember once I was describing this to high school students, and I was saying, look, you know, mathematics is really nice because you look at sort of a problem and you give a mathematical model. And everybody started laughing, at all the students. And I really didn't know why they were laughing. So, and then eventually, after the class, my colleague said, because you were saying you can look at a real life problem and change it into mathematical model. Anyhow, by the way, you can do all kind of things here. For example, you can change this to say, okay, the cat has an age, so 1 year, and then when you use this machine, then you get a dog of age 2. So it increases the ages, and then you get another set of puzzles. Okay, and eventually you'll see, I mean, these are similar in a way, but when I do the mathematical model, it goes in 2 different directions. Okay. Now, let me start with another puzzle, and this is a bit more serious. And I didn't know about this. It's not a puzzle really. It's a subject in its own, and it has its own books and heroes and so on. I didn't know anything about that until 3-4 months ago. But let me just tell you this one also. So imagine you have a grid. This is a grid. And you have 4 objects sitting here. So in the theory, they say 4 grains of sand or 4 chips if you're doing the gambling. And you have four elements, 4 objects here, and there are 4 edges here. So you're allowed to push the objects along these edges. So let me just do that. So what would you get is one comes here, one comes here, one comes here, and one comes here. Okay? Now, the way you're allowed to do this is that the number of objects should be the same as the number of edges getting out. So if you have less objects, they are not going to move. More objects you can still distribute. Okay? So if I do that, they say it's this node fires. So it fires and pushes the objects or the grains to the different directions. Okay, let me give you one more example and you see they become a bit more complicated. So imagine I have 4 objects here, 2 and 2, and let's do the game again. So the usual thing is 4, it gives me 1 here, 1 goes here, 2 already sitting here, so I get 3 and 3. Good. But now I'm introducing the notations here, or terminology rather. So this one, there were 2 objects sitting here, and there were 3 edges getting out. So this was stable. I could not distribute the grains here because there were 2 and there were 3 edges. Okay, but now when 1 moves here, it becomes 3. Now this node becomes unstable. So this fires 1 up, 1 here, 1 here, and the same story, 1, 1, 1. So if you look at this, I get 1, 1, 1 and 1 was sitting already here, 1 and 1, and then there were 1 comes here and 1 comes here, so I get 2. Okay, so, and then it becomes stable. Now I cannot fire any of these nodes anymore because the number of objects sitting here are less than the number of edges getting out. Okay, so now, I said sands, and this is the model, it's called Sandpile Model. So let me just write Sandpile Model. And just this model was introduced by 3 mathematicians in the 80s, Back, Tong, and Wiesenfeld in the 80s. My advisor in Germany was also named Back, but this Back came from Denmark, so a different person. And they introduced this model, and a couple of things about this model. First of all, they call this phenomena self-organized criticality. So let me explain what all this means.
Roozbeh, on the screen we can see that.
Okay. How about this? Good. So this phenomena, they call it self-organized criticality. What does it mean? Self-organized means you start with this model, say from here, and there is no force from outside. It just starts firing until it gets stabilized. And they prove that you always get a stabilized thing. Okay, so self-organized without any force from outside, you get here. Criticality means, and this is, they don't prove, they just tell you, criticality means that this is stable, but it's barely stable, meaning if I just add 1 more grains here, this becomes unstable, fires, and maybe there will be a domino effect, and then a lot of things would happen. Okay? So as you see, it's stable, but if I just add a little thing, it becomes unstable. So criticality means that it goes up to its critical point, and then it's stable. Okay, and then came a lot of papers about this model, but I just want to introduce also or mention another book by Back. It's called How Nature Works. So he was kind of very excited about these models and arguing that, look, a lot of things in nature has this kind of behavior. And then this book has not much mathematics in it, but it's just like a sort of philosophical. So for example, traffic jams, if the cars are here and these are the roads, well, obviously the car is going in all these directions. Or I just add COVID, of course, if it just spreads like this. Or in his book, bushfire, you know, this is the one tree and then it just, other trees catch fire here and it spreads. And I then look at the rest, but stock market apparently, you know, behaves like this and then it gets stable at some stage. Okay, but they prove 2 things about this. They prove in the first paper, so I can put here, say, 5 and here 3, and you see now,
Can you just for
Thanks. Good. So I put here 5 and I put here 3, and you see now this is unstable because there are more than 4 objects. So if this node would fire, this is also unstable. That also fires. So it's now you have a choice: either first fire this one and this one, or then the other way around, fire this, and then prove that it doesn't matter. You always get the same thing. So the model they have, it's called Sandpile Model. Sandpile models. But then, yeah, the order of firing does not matter, so therefore it's called the abelian Sandpile models. Okay, so you have to observe that, like a little theorem. But the next one, which is a bit more work to do, is that, as I mentioned, you keep firing, you always end up with a stable situation. But they prove that this stable form is unique. So it doesn't matter. So if you have here a very large grid and a lot of chips sitting there, and you just do this, at the end you always end up with the same distribution. So you have to prove this, but they prove that. So there is always a unique stable form. Okay, so that's what they did. But in order just to show you that, there's something here, it's not as easy as you see. For example, if I have a very, very large grid, okay, large grid here, and I put here 1 million grains, 1 million grains of sand, and you start distributing, so it goes like this, okay, and then you keep doing this. Can you imagine, if you look at first this one here, can you imagine in your head if I put 1 million grains here, what kind of shape I would get here? I'm going to show you, but while you are thinking, then you find the picture. And you see that, things becomes complicated. So here it is. So if there are $1 million sands here and you distribute, and then it just becomes stable, you get this sort of fractal shape. And in the literature, they say, well, that looks great, but we don't know why you get this sort of fractal behavior. So this is not explained mathematically, we don't know yet. At least the literature says, the book says.
So dark means more sand grains?
Right, okay, but yeah, I need to explain that. So you have this grid, and on each node, either there are 0 grains sitting, or 1, 2, or 3, because if it's 4, then it fires. So if there is 0, then I assign a number, a color. So if it's 1, I assign another color, 4 colors, and then you get this sort of organization. And then again, you can imagine that if I add one little grain of sand here, it's gonna just like a domino, just kind of thing. And then on YouTube, you see it really amazing. On YouTube, you can write a little program and it just changes so marvelously. Okay, so now that's that. Now let me change this a little bit. So this time you had these grids and then the elements move. Now I want to give directions so you know where you are going. You know where you are firing. So let me start with just one little example. So this time I'm looking at directed graph. So you have directions. So this is my system. So if there are sands sitting here and it fires, you know that it goes along this edge. It's not going to go along this one. Okay, so you have the directions. Or another sand grains would go and come back here. So that's one thing. The other thing I'm going to introduce in this model is that you have this node, it's a sink, i.e. nothing getting out. All the edges, all the vertices are connecting to this sink. And I'm going to say, once your object gets here, it's going to disappear. So if you are working with chips, once the chip gets here, it's going to disappear. You're going to lose your money, or the other way, the grains are going to drop out of the bowl. Okay, so that's another thing I would put here. So let me just give you one example. So what if I put here 4 and here 0? So you have 4u, and then see what happens. This fires. One goes here, so you get 1e, and okay, one goes here, and another 2 left, so I get 3u. Okay, so now I have 1 here and 3 here. This would not do anything because it's stable, but there are 3 getting out, so there's 1 here. But this one now again fires because there are 2. So the same story becomes 2u plus 2v. Again, one more time, this fires, so you get 1u plus 3v. Now in this situation, here I have 1 and here I have 3. So now you can guess here there are 3 and there are 3 edges getting out. So this fires. 2 of them disappear, 1 goes back, right? So here, 1 goes back, I get 2u. Now, same story again, u fires, 1u plus 1v, and then I'm here. This is the stable form, and by the theorem they prove it's unique. So, i.e., when I was here, say, if I had 5, and then here would be 2 and 3, then I had 2 choices to fire. But it doesn't matter which one you do, you always end up with this. And again, as you see, I have to do a little bit of work to get there. Okay, so they introduced this, and then came 10 years later, a very famous physicist, theoretical physicist, Dar, that in fact, my collaborator just mentioned that he recently got one of these fancy prizes in theoretical physics just a couple of months ago. Anyhow, so he came up with a monoid associating to these Sandpile models. So how is the monoid works? Well, imagine you have these vertices. These are the vertices of your graph. And here I put the sands, the number of grains of sands, so Ki. Okay, so this is one of the object, and another one, and I want to add them. Okay, so I put another one here. And the way I add them, I'm sure you know, just follow your nose. So just add Ki plus Ki prime, Ui, sum. And then, remember, you can always stabilize this. Okay? I can stabilize this at the very beginning or not, doesn't matter. But when you're adding, you add the coefficients and then you stabilize. So you get a monoid, i.e. I have a set and I can add them. And this monoid, as you see, just it's addition in the core, so it's an abelian monoid. Okay. So for any Sandpile graph E, and by Sandpile graph, this is a directed graph. There is one unique sink, and everything connects to that sink. So eventually, I can flush things out. So for that, you have the Sandpile monoid. So what is this monoid? Can this monoid explain, say, why you get this fractal there? Okay, so now you have a monoid, and this is a abelian monoid, so you can always complete that. So you can complete a monoid, and you get a group, abelian group. So completion of N gives you Z. Here it is very innocent, but sometimes when you complete, you lose information also if this is not cancelled. Okay, so this is called Sandpile monoid. This is called Sandpile group. Yeah, and well, so can you study this? Can you see these phenomena that you play there just reflect some behavior here? For example, in this Sandpile monoid, if I have an idempotent, okay, so E plus E happens to be E, i.e. I have an arrangement of, that's actually quite nice, I have an arrangement of these grains on my graph, and I put another one, exact same pattern, and then start firing, but I end up with the same picture. So what does that mean? Right? So in terms of monoid means you have an idempotent. Can you understand what is happening here? So idempotent. The other one is that what happens if this monoid is conical. What does that mean? That means if I have A and B, so I have two arrangements, put them together, and I get 0, i.e. then everything flushes and all the sands gets out. Yep. Oh, yes, sir. So I have two configurations here on my graph. I put them together, and then I just start firing, and everything just gets out. I get 0. If that happens, in what situation A is 0 and B is 0? Can you give me, conditions on my model? Okay. And what else that Dar observed when he introduced all this stuff? Let me just see if I can do something complicated here. Okay, so he had this and he had this GE, this group. First of all, the monoid and the group always are finite because if your graph is finite, there are a finite number of vertices, sands you can put here. More you can fire and get out. So this G is finite. And he gives a formula for this. So he calculates this and he realizes that this is the same, the number of this is the same as the trees ending in S. So let me just give you in this example what that would be. All the trees in this graph which ends in S. Okay, one of them is just this. And the other is this. So you have two trees end up in S, and you see this doesn't play a role. Okay, so if my model had 10 of these, still the monoid might be different, and it is different, but the group that you get is the same because you have two trees. And I was trying to remember, this is, I think it's called Birkhoff theorem. This is like 1800s, starting from 1800s, that tells you the number of trees on directed graph. In fact, it started with undirected and then improved to directed graphs. And the way Dar realized that is that he calculated this group, the formula for the order, and you see that this is exactly the formula of the number of trees. So I don't know, and I think probably that each of these trees, what element it represents, I'm not sure if this has been done or not. So the way he did it, just look at these two formulas, they match. So they said that, okay, so the number of elements in this group is just the trees here. And this is a very beautiful theorem of Birkhoff telling you all the trees. Nice formula for them. Okay, so now I want to stop here, change the subject to algebra, and then I'm gonna come back and put all these together, including all those puzzles that I have. Okay. So there is a notion of Libid Algebra, and people who are doing C-star algebra, I'm sure immediately realize what I'm doing here. Libid algebras and Libid path algebras. So let me just mention what it is. So William Leavitt, I think it's like 1957, published the first paper. He introduced an algebra, and the algebra is very simple. You get n symbols, get another n symbols, and get a free. So I'm doing very algebraically, you can do the C-star version of this. So get the free algebra generated by this symbol. So this is free K algebra, K being some field, if you want, just put complex number. Free, I just also put unital, K algebra. So this is free K algebra. And the relation he put here is that y1, yn, x1, xn is 1. Well, you see this row times this gives you 1. And as you would do in mathematics, just swap the orders and force this also to be, now this is an n by n matrix, so force to be 1, 1, IN, i.e. on the diagonals 1, everywhere else, right? So this is the algebra he introduces in one of the paper. And the first thing he proves, and you need to prove this, is that in fact this algebra is not zero. Because, well, here I can put whatever I want. What are the chances that this algebra will collapse to zero? Okay, so he proves this is not zero. Then he says that this A is in fact is simple. So he proves that. But if you look at the proof, you see that he has done more. He has done this. Any element that you give me in A, which is not zero, he finds two elements that in one go, if you hit from left and right, you get one. So it's much stronger than being simple. It's in fact purely infinite. Okay, so he does that, and then he proves what, and this is his motivation. He proves that this A is isomorphic to n copies of A as A module. So this was his motivation, to come up with a ring which is very far from linear algebras. That in linear algebra, well, one-dimensional space and two-dimensional space are of course different, right? So this is the first thing I think we proved in linear algebra, that there's a unique dimension. So, but here, it is possible you're walking on a line, but somehow you tilt your head and you're in an n-dimensional space. Here it is possible. So that was his motivation. Okay, so that's Libid Algebra. Then that was in 50s, and then came in 2005, because there is a C-star version of this called Confluence Algebra and then Graft C-star Algebra. Then in 2005, there were two papers quite independently to do exact same thing that people are doing in C-star Algebra in the algebraic version. So in 2005, Gene Abrams from Colorado and Aranda Pino at the time, a postdoc from Spain. And then 2006, Ara from Barcelona and his co-workers Moreno and Pardo came up with a Libid path algebra, which is the algebraic version of Graft C-star algebra. And I just give you quickly just a flavor. So here you have a graph E, a directed graph, and you associate an algebra. The Graft C-star algebra is the way you write this. But now I just do the LE, which is sitting inside that. So stay there. Then the first thing they proved that LE is simple if and only if it has certain geometry. So they describe the graphs which LE gives you simple algebras. Has certain, I'm not going to write certain properties. And then they see that, of course, if you plot this graph, one vertex and n loops, that gives you these Libid algebras that he introduced upstairs. And these have the property of that I want to get this Libid path algebra simple. Okay, so now this one was proved by Leavitt that as long as you have this algebra, it's simple. Now they give you all kind of graphs and they give you when they are simple. So it's beautiful. You can just change the game and you get whatever graph you want and then wonder what you get. So lots of paper came out. Here you just put your favorite adjective. Instead of simple, you put whatever you want. And somehow these relations are so natural that you get an if and only if, and you can describe the graph, which gives you this ring. Okay, so now I have to tell you just very quickly how they do this Libid path algebra. Again, if you are doing C-star algebra, I'm sure you have seen this. Just I give you a graph here. Okay, so this is U. These are the name of the edges. This is H, and so on. So this is your E. I'm just giving by example here. So you look at the free algebras generated by all the vertices. So these are vertices. Then all the edges, so pretty much you have all the information about the graph here, all the vertices and all the edges. And then I want, again, the edges going backward also. So in my graph, I have a chance to go backward. So I put this E star, F star. So these are, I incorporate this also into the definitions. Okay, so I get a free algebra here. So formally put these with no meaning next to each other and the sum of them. Now, what are the relations? The relations, the first two, is the one that it defines path algebra that I know it's been around for 60 years. So if you multiply two vertices, if they are separate, you would get 0. And if the vertices are the same, u times u, you get an idempotent u. So u times u is u times v different, you get 0. The other is that, let me just do with this e, if you multiply, because here I'm just having vertices and edges combining all these. So if you start with u, here it is, and then you multiply with e, you get e. So I'm just basically capturing how much I move. So you're standing on u, and then you travel along e, then how much have to travel? You travel e. Same story as e times the target. So if I want to write this intelligently, in terms of formula, it's a source of e times e equal to e range of e's. You do the same sort of thing for the star edges, the same story. So far you get a path algebra. Now the new relations that I put, and I get the Leavitt path algebra, and this is the notation, LE, and K meaning coefficients are coming from a field K, it's up to you, is this one. So first of all, if you travel along E star, and then you are back along E, it's as if you have not moved. So maybe I call it V, so V, right? So you go along E star and come back, then V, nothing happens. So if you do E star and anything else, you get 0. So you are not allowed to come back along any other edges. You have to come back along the E if you are traveling along E star. So if E and F are different, then it's okay. And the next relation I put here is that you see it's not symmetric. So you can ask me, what if you travel along E and then come back along E star? So exactly the opposite of this, right? So if I travel along E, come back along E star, you have to imitate this with everything getting out. So look, E is getting out and F is getting out. So I have to imitate that also. Then I retrieve U. So to me, it's like, use your own imagination. For me, it's like these are the lights, and then I have to pull all the way back to get here. Okay, so these are relations, and then I already spoiled the punchline. So if you had this and you put into LE, you get Libid Algebra. Okay, so the game started from there, and then you change your E and wonder what kind of properties you get. But one of the questions that was asked very, very early, and that came from C-star algebra, because the C-star algebra version is wonderful, is that if I hand you two graphs, then you get the Leavitt path algebras here. Can you tell me when they are the same? Because it could be that this graph, for example, and this graph, they look very different. This has only one vertex, this has two vertices, but if you calculate the Leavitt path algebras, they give you the same algebras. So if I give you two graphs, would you be able to tell me somehow they introduce the same algebras or not? In the C-star version, K0 would do that in certain cases for certain nice graphs. The group K0 that I will mention, in the group K group, would classify them. So they wanted to do the same here. They said maybe it just happens that if I have this K group, this is a group. This is an abelian group, whatever it is. So we calculate that. If they are the same, then maybe then LE isomorphic to L. So this is not true for all the graphs, but still it's unknown for certain kind of graphs. So those are the strongly connected. Everything is connected to everything to so to say. So a graph, everything is connected to everything, strongly connected. Maybe this is true, and this is still, and 18 years, we don't know. And funny thing, the C star version is correct. But the other, so there's two conjectures. I want to put it here. If you're interested, just drop me a line. Is that, well, there is a graded version, and this is something that I've been trying to do, the graded K theory, and this would classify, conjecture, all graphs. So if the K0, graded K0 is isomorphic, it classifies all graphs. It's still okay. Okay. Now, I mentioned two papers, the first two papers, and by now there are about 200 papers on the Libid algebra. But the first two papers are the one that I mentioned, 2005 and 2006. Gene Abrams and Aaron Lupino, they introduced the Libid algebra, and they only prove one theory in the whole paper, which means that they tell you when it's simple. That's it. The second paper, which appeared in 2006, tells you this fancy K group is, you don't need to know anything about the definition, how you do K0s and so on. You can immediately describe this out of the graph. So then becomes an undergrad, because for K group, you need to know what is the finite chain projective modulus, blah, blah, blah. But here, you can just get a graph and just introduce the group out of this one. But let me just tell you how it's done. And when I saw that, definition of this monoid, I said, how come this has not been introduced 200 years ago? Because it's so natural. So how do I define a monoid, graph monoid, assigned to E? Okay. And I give you again just an example. So imagine this is your graph. Now I look at the free monoid generated by just vertices. So get the vertices, there are 4 of them. The free abelian monoid generated by 3 vertices is nothing but n, right? So these are just direct sum of n, 4 copies of natural numbers. You just add them, that's right. But the relation that I put here is this one, that this U is the same as the sum of the adjacent matrices. That's it. And if you have more edges and more vertices, you keep putting these kind of relations in there. So, right, so this is ME for this example. And to me, again, it was very natural. So, the value of U is the sum of the value of, if you have $20 here and you distribute this to people, well, the value is the sum of this. So that we put here. It's very natural. So this is ME, it's a monoid, it's an abelian monoid. And again, remember, any abelian monoid you can complete and you get an abelian group. So you can see that the completion is this K0 group. So you have to prove this is not easy. In fact, it's difficult to prove. But at the end of the day, you can see that this K group is this abelian. Okay, good. Now let's go back to the story of Leavitt. So Leavitt started in 57 with the one that I mentioned. So these xi's and yi's. 1 to 2n, and then he put these, right? And then he called it, let's call it LA. And it has all these wonderful properties. Now then in 62 or something, progressively, he said, why should I stop here? Why should I just consider one row? I just put here matrices, right? Just bunch of, not one row, but matrices, see what happens. So he introduced L and M. Now, if I get it wrong, but there are that many I from 1 to n and j from 1 to m. Now, there are that many symbols that you work with. This is a free algebra. And then just you put here all the x's, you arrange all the x's, so x from 1, 1 to 1, n, x, m1, x, m, n, and then here you arrange all the y's, and you make sure that it matches so that you can multiply. I cannot read, I may read it. Okay, you multiply this, and the same story, you force that to be 1. But here, the 1 would be 1, maybe n times m, and then you replace this. Here you put the y's, exact same thing, and x, and then you force this also to be n times n. I think this is n by m, and then when you just do the replacement, you get n by n. Okay, so you get an algebra, and this is much more difficult, right? The first thing he proves that, again, this is not 0. Okay, so that's it. And then the other thing that is very surprising is that, look, when you're working with this one here, remember I just replaced these, swap these, and you should be able to see them. I really want you to see this. So when I swap this, and I force this to be 1, meaning 1, 1, 1, 1, everywhere else 0. So you have a lot of 0 divisors. For example, if x1 is multiplied by y2, you get 0. If x1 is multiplied with x3, you get 0. So in these algebras, you have a lot of 0 divisors. But what he proved is that this A is a domain. So here, it doesn't look obvious to me, but there is no 0 divisors. There is no way you can multiply 2 elements and it falls into this ideal generated. And then he proves, and this bit is not very difficult, he proves that AN is isomorphic to AM as a module, similar to previous one. So previous one was A1 isomorphic to AN. Here I'm just doing N and M. Okay, so you have this. And of course, the next step is that, okay, so I have this Libid algebra, and I have Libid path algebra. Now I have these new ones in 62. Can I give a graph version of that? Okay, and there is one. So very, yeah, so let me just give you a flavor how can I modify the graph, put it into this procedure to get this kind of algebras. So this is called the weighted Libid path algebras, and the C star version is yet to be done. So it's something that still needs to be done. Would be a weighted graph C star algebras. So the way you do this, and you might have guessed what I do. So again, you look at the graph E, F, H, and so on. Now this time you assign a weight to the edges. So I assign to E maybe 3, to F 2, and to H maybe 3. Okay, so for each edge you assign a number. So far not very difficult. So then in my head, if you're assigning 3 to E, so I have 3 edges. Here I have 2 edges, and here I have 3 edges. So far, no. Then, as before, you define an algebra generated by vertices, all these, and then you go backward. Remember, I wanted always to go back, so you have edges going backward, E star and F star. Now I have to tell you the relations, and I just put here samples that you see what I'm doing. Previously, what you did, you said E, E star, F, F star gives you U. Now, I look at this and think of this as 3 layers of graph. Layer 1, which are E1 and F1, layer 2, E2 and F2, and layer 3, which has only E3. And write those relations, previous relations, in each layer. So I write E1, E1 star, F1, F1 star, and that's 2 layers. Oh, I go one more further, E3, E star, and no, sorry, I made a mistake. I'm getting ahead of myself. The first layer is this one. So you look at just first layer. So you have E1, E1 star, F1, F1 star, and it gives you U. Go to the second layer, E2, E2 star, F2, F2 star, gives you U, and then third layer, that's fine. So that's one of the relations. Now, if you are doing this star, remember one way you go E star, the other is E star E. So if you do this, the game changes. Let me just show you here. You concentrate in one, and you go through the whole layers here. So you get H1 star H1, H2 star H2, H3 star H3, and then it gives you B. So there are many construction of graph star algebras, I'm sure you know. All of those, one way is the sum, the other way is just multiplication. Here is both ways, so they call it consecutive relations. Both of them involve sum. Okay. So let me call it LEW, and the punchline is that if you have n loops, this time each of the loops has a weight n, this is E, you plug into this machinery, then you get the algebra of Leavitt with these matrices. So I can recover their algebra using this machinery, and then the game starts for this one here. Okay, so you have all kind of weighted graphs, what kind of algebras you need. Just one example I give you. So if you have just one loop, but it has weight n, and you plug into that machinery, you get the usual one with n loops here. So this is one loop, weight n, gives you n loops with just weight 1. So this is the usual Libid path algebra, this is the weighted Libid path algebra. But then crazy things happen, so let me just put it here. In the theory of these graph algebras, it gets interesting if you have cycles. If you don't have cycles in the graph, it's a very simple algebra, very good, it's just matrix algebra. But in here, imagine I have just this graph which has no cycle, but I assign weight 1 here and weight 2 here, and this is not easy to see, and I can tell you, so you get, I still don't understand, I mean, this you can do by hand, and see that this weighted Libid path algebra is this one, and suddenly a loop appears. Something like that. And let me just give you oops, maybe I don't know, but anyhow, this is the one. And there is a paper by Raymond Poisa, so weighted Libid path algebras, an overview, archive, 2021. Okay, so I have maybe 5 minutes to change to just come back to all of these here, that's fine. Okay. Now, so you have these Libid path algebras. These are weighted. Remember, I just want to imitate what I had in the usual one, namely I want to tell you what is this case, this fancy case 0. So this fancy case 0 in the usual case that you have this, you could characterize using the just ME. And here I can do the same, ME and weight, but now I have to tell you what is this ME with weight. So let me just do this very quickly. So imagine with an example. So imagine this is your graph, U, V, W, Z. So as before, you just generate a free monoid using the vertices, so this, and this. Now, previously you said this is the sum of this one, right? So previously you said U is the V plus W plus Z. Now you have a weight. So let me just put here, for simplicity, weight 3, and all of them has weight 3. I'm not going to change the weight. So the edges getting out of U all have the same weight. I could have done 2, 1, 5, but then the definition of monoid will change. So they have to have the same weight. Then the way I define it, and you might have guessed, I just put here 3U. So this is the definition of a monoid I introduced here. So the usual as before, the value of u is the sum of this, but if it has weight 3, then I say 3u is this. Okay? And of course, this is a generalization of what I had before, because if I have all weight 1, I'm back to the usual. All right, so I'm almost done. Now I want to bring all of this together. First of all, let's go back to these puzzles. The math puzzle, very, very beginning. So, this one here. Maybe both of them. Okay, so remember this, that a cat becomes a dog, so I can write a cat becomes a dog, and a dog becomes a cat, and a dog and a rabbit, and a rabbit becomes a cat and a dog. And you know what? Then you have a bunch of animals, so I can just say add as many as animals you want. So this becomes a maybe 3 cats plus 4 dogs plus 5 rabbits. So this becomes this free monoid, and these are the relations. This becomes my monoid, and the question was, can you go from 1 cat to 4 cats, i.e. in this monoid? In this monoid, it's possible to solve, and I get 1 cat is 4 cat. Now, this monoid, let me just introduce now this graph, a cat and a dog and a rabbit. And you see a cat becomes a dog, so I just put here, a cat becomes a dog becomes a cat, a dog, a rabbit, and a rabbit becomes a cat and becomes a dog. So now you have E, and stare at this, the ME is the ME of this graph, okay? So, look, I have not given you the answer that if this has a solution. I'm just reinterpreting into a model. But in fact, once you have this, then comes confluence. I mean, a couple of things you can prove here, and then it's easier to answer this. Now, for this one, it's the same story, but then you see I have 3 rabbits, 3 cats, 2 dogs, then it becomes a weighted graph. So I use the same story here, so rabbit, then cat and dogs, and the rabbit goes to a cat and 2 dogs. Oops. And I just put only this bit, you can complete it. But in order to capture it, look, I get 3 rabbits, so I put here weight 3. This is my E with the weight. And you can see that I did this trick here. I can do exact same thing. And ME W is this MEW becomes a model for this one. And the question becomes, inside MEW, can I give you 3 cat and I get 4 cat? Is this correct? Now, the nice thing about this is that now you have an algebra associated to this. You have this E, you have an algebra, and you have this monoid. These are these K groups that I mentioned, and that's ME. So I assign an algebra, and its monoid, which comes from projective modules, becomes this monoid here. For E with W, I have this Leavitt path algebra, and its monoid becomes ME with W. And then I'll finish with now, only 1 minute. So the only thing left to put all these together is that Sandpile. And for the Sandpile, remember you had this Sandpile graph, E. And you have this distribution of the grains there. Then you have the Sandpile SPE. You can prove, and this is what we did with Gene Abrams, but it's really his observation. is that you can prove that this Sandpile is in fact, it's exactly the monoid, that K group that I said. So before you get the K group, you have a monoid coming from the finite joint projective modules. Okay, I'm just giving you a flavor of this algebra. So you look at this graph E, you look at the weighted Libid path algebra almost, so yeah, this one, okay? You get all the finite joint projective modules, that gives you a monoid, and that monoid happens to be the monoid coming out of these sands. And this I don't understand, because here you're working with projective modules of algebra, and here you're just working with in this game that you play. Then of course, then the GE, which was group completion, becomes exactly the K theory of this weighted Libid path algebra. And I just finished with that. Okay, so now you have this model, Sandpile model. You have the monoid associated with that. Now you have an algebra, and this is what we call Sandpile algebra, because it's kind of also, you can see that this is kind of a uniquely defined, this algebra. So now you have this Sandpile algebra, and then the game starts here. Can you describe, say, so the properties of your model in terms of maybe the ideals of this algebra? Or, you had that grid with all that fractal. What does that mean if you look at the algebra? And then what kind of structure you have inside the algebra? No, I stop here. Thank you.
Thank you, Roozbeh. Very interesting. Any questions or comments? Online in the room?
So if you have this graph monoid, is there a easy or is a definite way to prove when two vertices of this graph are the same?
Yeah, say it again.
So we have this graph monoid where you just say, the vertex is the same as the addition of all its neighbors.
Right.
And is there a way to show whether, if we have two vertices, whether they are the same?
Well, I don't think you can immediately say that. So, for example, U, V, W, and Z. U is the same as Z in that monoid, right? Because U is this sum and Z also this sum. But if you can immediately see from that monoid, I don't think you can. The thing that you have, I said that can you 4C is equal to 5C, can you solve that equation? What you have is this confluence lemma in this setting, that if A is equal to B in ME, so A is just sum of a bunch of vertices, B also sum of vertices, and then being equal means that you keep just using these relations of sum, but in all kind of ways to get from here to here. You say that if they are equal, then you can go in one direction, transform these vertices in one direction. For example, V, you transfer here, there is nothing to do. But if you have U, you just put this. But in one direction, you move, and here also in one direction, you move, and you get to the same thing. So two things are equal on the level of monoid if you can push them in one direction and get to the same thing. So these kind of tools you have. Yeah, but if you give me two elements and they are equal, I cannot immediately tell you, how you're sitting in the graph.
Yeah. All right. Anything else?
Do these, the Libid algebras have something to do with Thompson, right?
Right, Thompson groups, yeah, you can describe it. Yes. Those are the Libid path algebras, yes.
Can you say a bit more about that?
So let's see. Okay, yeah, So even for
Maybe
yellow,
later.
yeah, so no, I have to look at it. But you can describe the Thompson groups coming out of the elements, sort of infinite paths of your Ln. Just Ln, you can describe the Thompson group from there. But I have to look at it to see how it's done properly. Yeah, but you can do that, yes. In fact, the paper is by Pardo, so it describes Thompson groups and Libid path algebras. And the follow-up by Sorensen. So in fact, Sorensen was in Illinois when he wrote Sorensen and forgot the other. So there are two papers in that direction. But I need to look at it to see exactly how it's done. Okay.
I had a question too, if you don't mind. So that was a very nice description of K0 of something. And not that I know much about K-theory, but there are higher K things as well, right? Do you get a description of those in this framework too?
You can, I don't think you can get it coming from the graph, but you can see that they sit in a non-exact sequence. So K2 goes to K1 to K0, and the K0 comes out of this description of the graph, but not K1 and K2, I don't think.
Right.
But there are papers again on this, yes.
Right. Okay, does anybody else still have any questions or comments? If that's not the case, let's thank Roozbeh and everyone else of the day one more time. And you can stop the recording there.